start. So we are going to do not the syllabus. We're going to do this one. Is that the? Yeah, that's the student one. Okay, cool. And I'm going to need this Desmos on the side here in a few minutes. Let me zoom out a tiny bit. So limits. We haven't done limits in quite a while. Did y'all do limits in Cal 2? I can't remember. But like in Cal 2 you had them? When did you learn L'Hopital's? Was that Cal 1? Oh, then y'all are fine. So yeah, we're gonna do L'Hopital's for sure today. But that's the main limit formula that like we ever need. There is one new one here in Cal 3, which I'm going to show you, but it's more of like a concept than anything. Anyways, all this stuff I'm sure you've seen before. I'm not really worried about that stuff, okay? And add on to this L'Hopital's rule, and you're good to go, right? So let's just do it. So it says find the limit. But now notice that we got X and Y. Oh no, I'm super scared. It's not really that hard. What traditionally, when you don't really know what to do or where to start, what do you do with those two numbers? Plug it in. Thank you. Super easy. Don't go complicated. Thank you. Just plug it in. So here we go. In fact, I'm going to not even touch that. I'm going to put it all right here and hope for the best. So fraction action, negative 2x squared. Okay, I need to be able to type it, of course. This is always a go-to, a starting place. If it doesn't work, fine. We'll try something else. But try at least to plug it in. So we plug in two numbers, and there you go. Like, let me confirm. I have this one up right here. Yeah, see, we're done. I just flashed the answer. It's done. That's it. That was all we had to do. So what did you just learn about limits? Plug it in. Why didn't they tell you this in Cal 1? Oh, okay. That's the ones I get in trouble for. So, yeah. It's the secret that no one wants to talk about. Good with this, though? Happy times, right? Let's try another one. So here, plug it in, right? Of course, now we're going to be disappointed, but I want to see what Desmos says. So this is always a good starting place. If I don't know what to do or I'm kind of confused, let's just plug it in, see what happens. So I got x equals 6. I got y equals 0. Okay, perfect. Now, I know the answer is not undefined. There's actually a thing for it, but I've tried to plug it in. It doesn't work. Now let's go and do something else, right? So the problem here is that 0 right there. The 6 is no problem. It's the 0, right? Because it's making the whole thing 0. So there's a couple ways we can go about this. I'm gonna give you one thought. What if, and simply because they're both the same, what if I just do a u substitution? What if? Kind of strange, but let's try it, right? So if I had that, I would have the limit as u approaches what? 0. Because if you have this and you literally plug in the 0 or 6 times 0, you get 0, right? So u would be a 0. So we're going to 0 of sine of u divided by u. And this is just one direction that we can go, one thought, okay? Have you seen that before? Yeah? What is the answer? I know, right? You've seen it, and it's like, I know it's something. This one's a special one. 1. 1, yeah. Let's go and confirm. 1. Yeah, it's one of those weird guys that we had to memorize, if you remember. But why did we have to memorize it? I think it's because we didn't have L'Hopital's. Like, real quick, let's just do L'Hopital's right quick, okay? So the limit as u goes to 0. What's my derivative of sine? Okay, sweet. And what's my derivative of u? And if I plug a 0 in there, I got cosine of 0 equals. So it was L'Hopital's rule, even back in Cal 1. They just didn't tell you that. Ha! They said memorize, and then never mind. I know. I don't know why, educational wise, why that is. I like to have all the stuff, all my tools ahead of time. That's just me personally. But you know, gosh, man, I did not prepare you for that, did I? Mm-mm. no, you take Chad's class, you were underprepared for that. Good with this though? So just a different way of thinking about it, right? So what do we do with this one? I'm gonna just have y'all tell me what I should do. All right, all right. Hey, hey, let's try it, man. Yeah, I'm always about trying the easiest way possible, right? And we got a Z this time. Oh no. As if my whole world is falling apart. So I got an x is equal to pi. I got a y equal to 0. I got a z equal to 7. Oh, well, we got something. Now we're okay. Right? Isn't that how we're supposed to do it? First off, we got a number. We got a number. That means that we do need to plug it in. Let's try it. 1 divided by pi. So here's what I would suggest. I would suggest no Desmos. I know that sounds kind of weird, but literally plugging it in by hand might actually give you a nice answer. 21? Oh, for reals? Oh. Okay, so 21, and then yeah, e to the 0 is a 1, and cosine of 2 pi is a 1. Oh, okay. So yeah, let's flash the answer. Yeah, okay. So why did Desmos give it to me wrong? Did I? Oh, you know what? No, I was thinking. Oh, look. Ah, oh, it gets me. Okay, that's fine. That's fine. Every time. Yeah. All right. I thought I was so prepared for the day. I've looked through this like 3 times now, and I was like, okay. All right. Cool with that though. I should though. I should, right? True that. True that. All right. This one is the one that I got rid of on the homework. Okay. Yeah, I actually like none of this. None of this is good anymore. I just want to give you a brief about why. I think it's very confusing that they're wanting to give us these Ks and we have to force K into their paradigm. And I just didn't like it. There's only 2 questions about it on the homework. I deleted those. I just don't care anymore. Okay, cool. Okay, good. They're gone. Moving on. This one's way better. So there's a lot of blah blah going on here. There's a lot of blah blah. But if you kind of see it, they're talking about the sandwich theorem. I want to show you graphically what that is. So back in the day, you had something kind of like this, and you want to come on either side of it and kind of sandwich it in. So it's got to be between these 2 values, or between these 2 functions. And that's kind of what they're doing right here. They have this guy and this guy. The thing is, though, and this is what's so funny for us, they give it to us. Squeeze theorem. There you go. Yeah, squeeze theorem. Yeah, see, you know it more than me. Sandwich, squeeze, whatever you want to call it. Starts with an S. So we got a top and a bottom, essentially. I want to use theirs without having to do it my way for a second, okay? So they say, knowing that it's this and that, what's the answer going to be? Well, what would you do if you had this and you had this limit right here? What would you do with these 2 guys? Plug it in. Yes, this homework section should be this easy. It should not be that difficult. And if it is, you tell me, and then I'll probably just delete them problems. Oh, it's 0. So we got a 1. Out of this one, we have equals 1. Out of this guy, when I plug it in, I get 1. So between 1 and 1, what's the answer? There it is. I'm just using what they gave me. I'm just using what they gave me. There are other ways to do this. There are. But that way is not as exciting. Are you okay using those two things they give you? What if they didn't give it to you, right? Couldn't we still figure this out? Limit as x and y both approach 0, 0 of this doodad. What did I do last time? When they are the same identical thing, that's like a trigger. It says, I probably got to do u sub. It doesn't always happen like that, but surely this time. And if I plugged in 0, 0, what would I get? 0. So we're going to 0. We're saying the limit as u goes to 0 of arc tangent of u over u. And that is why I needed the formula book, because I couldn't remember that. The derivative of arctan. What the heck is that thing? So yeah, let's do some L'Hopital's. And so we're going back. We're saying the same limit here. Derivative of arctan is u prime over 1 plus u squared. And then what's the derivative of just u again? Well, technically, it's u prime. But that's the thing, though. It's 1. And so that's the thing. I need to just say it's 1, just like I did last time. It's 1. So u prime, what do I actually put right there? 1. Let's not go too crazy here, right? What's the derivative of just a single letter? It's just 1, right? And when I plug in a 0 there, what's the answer? It better be. It better be. Cool. So blah, 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 blah. Just plug it in with what they had, right? But if they don't give it to you, we got other techniques, and we've now seen those techniques twice. I hope that 1 is legitimate.
Well, no, other than the 1.
Yeah, generally. So I haven't truly explained what we're really doing here, and because we haven't had the ability or time to, like, we haven't had the need for it yet. So you're breaking onto something here. You're cracking some ice that's good here, okay? So let's talk about that. I want to get this out of the way. Go away. Thank you. All right, let's pause for a second, because this is the first one that is truly calculus 3, okay? It's different than the rest. You see, we don't have one variable that kind of like just does a u sub. I can't just say that now, right? It's not the same. And when I plug in 0, most certainly it's going to go to something bad, right? So, okay. So there's definitely some ways we can go about this. But I have to explain what in calculus 3 we're talking about. So far, I've just said, oh, well, there's two numbers, right? Just plug them both in. Easy enough, but what we're trying to do is see what's going on with the graph at the origin. And this is like, a 3D graph and all that kind of fun stuff, right? We've been seeing that in the other sections. So what's going on right here exactly? Well, the limit, if you remember how limits work, this is just a 2D limit, okay? They're saying find the limit. We come from both sides. I'm going to write that down because that's important. We're coming from both sides. Y'all remember these limits, right? It says limit as x goes to 0 from the right, x goes to 0 from the left, that kind of thing. So like we're used to doing left and right, and then I say I need both. Both sides get the same number, we're good to go, right? Isn't that how that works back in Cal 1? So now in 3D land, I need to come at it from all sides, not just both sides, all sides, every single way. And that means coming in at the cardinal directions, 45 degrees, 30 degrees, 60 degrees, 1 degree, 2 degrees, 3 degrees, 4 degrees, 5 degrees, every degree, 1.1 degrees, 1.2 degrees, 1.3 degrees, all sides, all the ways, because, and this is like a more graphical representation of what it could be. I'm going to try to like do this here for a second. We could have a hole, but that hole only exists in the first quadrant. So I'm like, oh, everything's fine, everything's fine, everything's fine, everything's fine. Whoops, and it doesn't work. One way it doesn't work, the whole thing doesn't work, okay? So there could be this like hole, right? That's what we're talking about, undefined location, but coming only from one direction. Who knows? We don't know that until we test them. How are we going to test all those points? How are we going to test every direction? You see, that's the fundamental theory now. How do we do it? You tell me. What do you think? So that's one. Define y. Let's say y equals 0. So y equals 0 means for sure, I'm going to use different colors so you can kind of see what I'm talking about. We're for sure on this axis. And then you can say both ways. Sounds legit, but then you didn't go this way or 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 this way. But that is one thing. Maybe I say x equals 0. Try it again. These are all fine, but it's not enough. What do I do? I have to what? Oh no, that's too complicated for me. That sounds legit though. That sounds good. Yeah, that's above my pay grade. How about this? Why don't we switch to polar mode? And look right here. This is kind of telling you that. What is that kind of leaning towards? Circle. Circle. Yes. Now, not every single time they're going to give you such a nice circle. But what if instead of going 0 to 0, like 0, 0, 0, what if I were to say instead, I want my radius to go to 0? And so in a way here, I'm going to say that theta is anything. Theta is anything. And rather not anything, everything. And that's the key trick here. I want to now come in towards 0 from every direction. Any direction, any theta. But I do know at least my radius is going to 0. Yes? This is the kind of the leap here. We've already been doing u sub, and this is very similar how I took two variables down to one variable, right? That's what we're going to do here as well. I can't say r is just like x or y or x times y. R squared is x squared plus y squared. Isn't that true? Isn't that a formula? So that's what we're going to use in order to make this thing work. I'm going to say r. Let's replace it with r and theta if possible, if needed. I'm going to rewrite all this. So here we go. I'm going to say now the cosine of, and now I've got to actually rewrite this thing in polar form. Let me give you some more formulas if you remember them. X is equal to r cosine theta. Y is equal to r sine theta. Remembering these guys? Tangent theta is equal to y over x. All these formulas we're going to have to use. So in the bottom, the easy one, what do I put down here? R squared, very good. R squared. But now the top is kind of tricky now, isn't it? Would you rather factor or would you rather just dump it all in? Dump it all in. So what do I do with this x cubed? R cosine theta cubed. Exactly right. Exactly right. Minus, for my y value I plug in, r sine theta cubed. Exactly. I'm going to change different colors now. In fact, I'm going to get rid of this other parentheses. Yes. There it is. I'm gonna erase my pictures. They're just gonna end away, but because we're gonna do the math now, and I'm gonna switch colors too. Okay, awesome. So yeah, I basically said x, I have a formula for that. Y, I have a formula for that. R, basically, right? And now I have this big mess. Surely we can do something to simplify this first. What can I do inside? Okay. I like that. Ooh, now that we have my, oh, no, you're right. Factor it out. I like that. We got it cubed, and we have it cubed. And we still have a square in the bottom. What else can I do? Heck yeah. Sounds good there. Get rid of that fraction entirely. Love it. Now, you might be asking, hey, Chad, you have a theta in there, and we're not plugging in a theta. What am I going to plug in for theta? That's the thing. Theta's everything. Anything. It's not just, oh, it's 0, it's 2 pi. No, it's literally all numbers. So we have to have an answer here in just a second that kind of accounts for that. At least I hope. Okay. At this point, now that I've simplified, what do I do with the r? And what do I get? Cosine of 0 makes a 1. And let's verify with the answer here. Again, I got rid of that one. Yep, there it is. No, that was the wrong one. This one. 1. Yeah, all of this right here doesn't matter. It did not matter because this guy right here equals 0. It doesn't matter what these guys are. And that's a good thing. I allowed for the problem to come in from any angle. I said, just give me an angle, any angle, everything will be fine. And it said, yeah, sure. Plug in a 0 and it all disappeared. That was perfect.
It doesn't that work because you can also plug in any like degrees or anything like that into the sine and cosine, but still be.
And you still get the point. You get the same number every single theta. Plug in a new theta. Plug in a different theta. Come on, plug in another theta. It doesn't matter. You're going to get the same answer. And that's the good thing. Cool? Now, sometimes it could be that we don't actually have that. I got to say that. Once in a while, we could get different answers, and we'll see. If it doesn't cancel, then that would be a problem, of course. Good luck. It is not. Basically it won't work. I would say if you had a 1 here instead, then these thetas would take over. What theta do you plug in? I have to plug in them all, and I'm going to get different values for the cosine of that. Like you could just simply plug in a 0 for theta and a pi in for theta. You're going to get different numbers. Yeah, you're going to get different numbers, and all of a sudden it says no good. Right? Very good. That was good. Good talk. Okay, so this one scares me. This one's very similar. I want to see what y'all come up with. So y'all do that one. This is a you do. It's the same as last time. Same formulas. Just want to see what y'all get because I was nervous about it. I'm going to give you all the tools here, which you already have, of course. Oh yes. Oh yes, getting very nervous. I have an idea what the answer is, but we're going to see. Like I want to talk about it so bad. But I know y'all are busy doing stuff. Should put my water down here. Got an answer?
Oh, I'm kind of stuck.
Uh-huh.
What I'm thinking about is, do we do L'Hopital's rule? Okay.
What can you do L'Hopital's rule with? That's the problem. It doesn't truly have that form. And this is where we need to think calculusy. Y'all ready? I could wait another minute. I know, it's super fun. This is the greatest thing ever. So yeah, this makes me super nervous, but in a good way. I think that y'all are all probably okay saying that that's r squared down there. Same as last time. And then I plug in for my x and y. So basically I'm saying the limit as r goes to 0, just like last time, arctan of r cosine theta plus r sine theta, then all over r squared. Now, absolute value signs are, they're just so loosey-goosey. Let's talk about a circle. Can you have a negative radius on your circle? Not really. So would you be okay with me factoring out an r from each of those absolute value signs? Good, good. So yeah, and it might not be the perfect math, but conceptually it makes sense. Because I did that though, what can I do with my r's? One of them, not both? Darn. And that's now a new problem for us, isn't it? Okay. Let's pause for a second. I know value signs for sine and cosine. Can I get negatives out of those dudes? Yeah, you can. Oh man. But what if it said cosine squared, sine squared? It'd be fine. So the problem is that sine and cosine by themselves are still negative or positive, and so I need to say, hey, it needs to stay positive somehow. Okay, so I can't get rid of those. But there's nothing really else I could do with the r. What if I get r and plug it in? What do I get there? I get undefined. You know, this is the interesting thing here. Undefined in calculus. What does it really mean? Say it again. Correct. Okay. How do I? What mathy term can I use? Quick one. And it's a calculus one. Okay. It's not something algebra people know. Okay. Maybe they do know. Infinity. I know that's a weird thing, but and nobody tells you these things. These are the things that nobody tells you these things. If you go back to undefined, why is it undefined, right? So undefined, as we know, is 0 in the bottom. Yeah? Well, let me take the limit of that. And so rather than putting a 0, I'm going to put 0, 0, 0, 0, 0, 0, 0, 0, 1. And I want to see what that looks like. So I got 1 divided by boom. And notice that is a number, right? You get if you want me to take it back some so it looks more regular, look. What am I actually going to? Into infinity, right? The more smaller the bottom gets, the bigger the overall thing gets. So I just call it infinity. So whenever they say undefined, it actually means infinity. If they didn't tell you that in Cal 1, I'm sorry. That is a very key concept in calculus land. Good. So then, what's arctangent at infinity? Literally plugging that in, what would you get? I know that sounds like you can't plug in infinity. Yeah, you can, especially to arctangent. It's like, no. But watch this. Watch this. Did you notice? The numbers stopped changing, didn't they? Have you seen that before, 1.57? Oh, wait, degree mode. Yeah. It's pi over 2. It's pi over 2, 1.57. And I'm going to show you why. I want to show you why. I don't want to just leave you in the dark here. The arctangent graph, I think I got my thing wrong there. It looks like this. This is the arctan graph, and it actually has a horizontal asymptote at You guessed it, pi over 2 and negative pi over 2. And so I'm saying take the arctan to infinity.
That's what I was about to ask. Is would it be both positive and negative pi over 2, since technically 0 would be both going negative and positive?
Well, that's the interesting thing. In the top, and they made very clear about this, what would I get from the top? A positive or a negative? From the top, I'm required to get a positive. Does it make sense? So undefined, yes, but it's technically positive infinity. It has to be. Therefore, positive pi over 2.
So since it's in absolute values, that's why we get a positive
Exactly.
instead of both positive.
That's exactly. Because if we had only sine and cosine by themselves, that'd be negative or positive. Who knows? Sometimes 0. But no, this time it's different. This time it's different. It had to be positive. It had to have an answer. Cool, right? So that was a whole bunch of leaps, wasn't it? And I said that was a you do. But I mean, in a way, I wanted to see like who you had for Cal 1. Yes. Perfect. 100% that. Yes, I will repeat it for the folks at home. Y'all are all here, so I know. For the next semester. Right. We're changing into polar mode, and we're trying to find a way to ignore the theta. Because, again, the theta should disappear. Should. And then we get an answer, and we're done. Sometimes it's crafty, right? This one's a little bit more crafty than others. Other ones are more just plug it straight in, right? But it is something. Very good. Very good. And then we're done. That was it. That's limits. I love that concept. I think it's so cool. But honestly, you just have to kind of do it a lot on your own. You know what I mean? To kind of get the feel of it. And that was it. I want to move on. Partial derivatives? Oh, yes. Yes, partial derivatives. Let's talk about it. So, and I'm going to go super slow on this because this is a vital topic going forward. Limits, you plug it in, we're good, right? This one here, though, you're going to see this throughout the rest of the class. So let's really sit down and hang out with it. So partial derivatives are regular derivatives. You've been doing partials your whole life. You just didn't know it. So whenever I say f of x is equal to, I'm just making it up, x squared plus 9x minus 1, and you say, hey, find a derivative, right? Super easy. You just took a partial derivative. Did you know that? A partial derivative is a normal derivative, but in calculus 3, what we're doing is we're adding in some random variable. Oh, let's just call it y. And it doesn't really matter, because if it were multiplied by y, then you get a y in the end. Instead, let's just say I had a plus y over here. So I had a plus y, just some other random letter. I'm just using y. What would just a plain old number go to? Would be 0, right? It doesn't have an x. Oh no, I used y. So what? I used a letter. I can use z, I can use t, I can use a, b, c. Doesn't matter. It's just another letter. And you treat it just like you would not your x in your derivative. Okay? So another example. I'm going to show you another one. Let's just say that I had, let's do, and I'm doing f of x on purpose. I'm being silly on purpose, okay? Let's do x times y squared plus x cubed times y. Perfect. Just, I want to do derivative. Plain, normal, regular derivative. What would I get out of this guy?
So that would be the
No. We're doing simple. We're taking derivative in terms of x. Don't.
just be y squared.
There it is. This guy goes to a 1, and that was a number. You just leave him alone. What about this one right here? What would we get? 3x squared, and then you have a y because it's just a number. Yeah. What if I here? Let me just add a y over here. 7y. Even 7y. What would I get out of this? Derivative in terms of x. It's just another number. It's just another letter. Doesn't matter. It has nothing to do with your x. Right? And I'm calling it y. Just that we have a letter. Okay? Does it make sense, guys? We've been doing partial derivatives our entire lives. Okay, well, for the past few years. But so don't overthink it. Don't overthink it. It's just a number. You can think of that y like as if you were saying it's a 6, and you would put a 6 right there, and it would be fine. Okay? Are you feeling me here? You feeling me going forward? Keep it simple. Very simple. So if it were so simple, why do they make it complicated? Why are we talking with these weird symbols and stuff? Because we have to go back and forth a lot, okay? So now that you know the secret, that's the secret, okay? I'm not doing anything new here. Let's talk about what all this other terminology is going forward. So they have this new character, and this is called del. It's not delta, because delta looks like that. That's a delta. So then this is just del, okay? Capital delta is a triangle looking thing. A lowercase del, or I'm sorry, an uppercase del is an upside down one, which we will see later, okay? So this is lowercase, this is, lowercase, this is uppercase. Cool? It's not a real letter, by the way. Del is just not delta. It's just the opposite of it. That's it. We ran out of letters. Let's just make something up. And I'm dead serious about it. But all of these here represent D. And what does D mean? Derivative, change, rate of change. I'm just going to say derivative. Derivative, keep it simple. D stands for derivative. So we got derivative. That's all what this stuff means here. Derivative. So we're going to do derivative of f in terms of x. This is very similar to saying df dx, or maybe you've seen dy dx, right? Or this is all Leibniz, d dx of f of x, d dx, oops, I wrote a y, d dx of y, did it again. So none of this is new. This is the same thing that we've been doing again and again and again. I'm just saying it's df dx or dy dx, whatever you want to call it. Cool? Cool. Nothing new. Good? I just want to keep stressing that. You put a d in, it's the same thing. This, though, is the Newtonian version. You know, normally we say f prime. Well, I can't do that because now we're going to have a lot of different letters going on. So now I'm going to call it. I'm going to say, look, I did it in terms of x. And so that's very much what we were doing earlier. Give me a second here. Just giving you some more demos, okay? What if I had x squared? Super easy. And I said, hey, find the derivative. We always say prime. But now it's too ambiguous. We're going to have to say, I did it in terms of x. A subscript, yeah. A subscript letter for what derivative you're doing. Yep. And what if I wanted to take the second derivative, right? I'm going to say, double prime. No. You say xx. Remember, this is Newton here. How many ticks can you get? I'm just joking. That was an ambiguous answer there. I think I used that word too many times. Anyways, are y'all getting me, though? It's just a different notation. That's all it is. Okay, good. Erase. Erase. All right. Now, we also have the y's, and that's why we're going to have them mixed up. And so this is the real, confusing part. And oh my gosh, can it be any more confusing? So Leibniz and Newton, they yelled at each other for a long time. Do y'all know the history of that? And so neither of them knew about partial derivatives, but I'm just telling you that they were doing it anyways, right? It was always partial derivatives. But how we go about this is we go this way with Newton. We go this way with Leibniz, and that will catch you every time. It caught me so many times. You're going to go, derivative of this, derivative of that. No. It's the flip. Yep, you got to flip it. So Newton is the correct way. Leibniz went backwards. Okay? Can I show you why, though? I know this is all a history lesson. Y'all hate that stuff. I'm so sorry. Because Leibniz, it's functions of. Yeah? I'm replicating this one, by the way. How many D's do I got in the top? 2 of them. How many F's in the top? How many D's in the bottom? 2 of them separated, I guess. And then I got an X and then a Y. Notice that this guy here came first. This is the first one that we're doing, and then this is the second one we're doing, right? Composition functions, blah, 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 algebra. And so then I said, oh, well, I did my y, and then I did my x, because I started with y, and then I did an x. But now in Leibniz notation, this looks backwards. Okay? Okay, good. I don't think they expressed it well enough down here at the bottom, but yeah, that's why you have me. So let's do some of this together, because this is like the utmost fun in derivatives. Because guess what? It's just derivatives, and you've done this so many times already. Look, I'll even put in Latin characters so that you feel better about it, okay? I'm serious. D dx of my function f. What would be my derivative in terms of x? Easy. Uh-huh. 7 times 1 times y. Yes, exactly, of course. I'm just making a point about it. And then all of this is 0. It's just a number. It goes to 0. That's it. You just did it. You've always been doing it. You've always been doing it. Don't tell the Cal 2 people this. You've always been doing partials. Back in the day when we were using TI-89s to do all the calculus for us. Sorry, guys. But back in the day, how do you do a partial derivative? You just do a regular derivative, and it was the same. In the calculator, they didn't have partial derivatives because it was just a derivative. What would it be for y? Since we're taking the derivative of y, wouldn't the first one be 0? 0. Plus 7 or minus 7x. Times the 1, yes. And then plus y. Perfect. There it is. Let's go flash the answers. Oh, there was my pi over 2. Guess I got it right. There. Did I get it right? Looks good. That was supposed to be an equals, by the way. You've been doing these your whole nothing new here. The only thing that would be kind of different is the notation's a little confusing at times, but we get over it, right? It's like an accent. Somebody says something in an accent, you're like, okay. Like, that's just okay. That's what do we do? Good? What do they look like? Mm-hmm. It's a slope. Just like a regular derivative, it's a slope, but in a direction. It's the slope in the x direction, in the y direction. Yeah, so cardinal directions, I guess. Yes. So, and ultimately, that's what a derivative does. It gives you a number, because you have to plug in a number to get a slope, right? Same thing here. If you want to have like curve sketching for this, that is not in this class, because it's already complex to make a 3D shape. Now let's throw a derivative 3D shape. You know what I mean? But yes, that's very good. They're slopes. They're simply slopes. There's probably cool stuff that happens. Good thing we have Desmos. We humans can't do that. I want y'all to do this one. This is a you do for sure. And while y'all do it, let me go get my water. I'll be back in just a minute. following the video. I know. Do y'all have answers?
I do. For the derivative with x,
Mhm.
x, that would be 16.
Whoa. Probably, but can you give me like an easy step first?
Okay, so first starting off with the power rule, it'd be 4
Very good.
7x minus 4y to the third power.
Perfect.
7.
There you go. Just 7. Yes, you're right. Pause. So you're exactly right. It's power rule. We've done this a ton of times. 4 comes down to the front. Leave the inside alone. Leave the inside alone. Third power. Take the derivative of the inside. And again, we're only thinking of x's. So x goes to 7. Easy. The y goes away. It's just a number. What did you say, 28? And there's no need to simplify anymore. Okay? And if they want you to, it's no good. You tell me. I start yelling. What about this guy? What do I do?
Same thing though with respect to y.
So my derivative would be, oh, there's your 16. I see now. Cool.
Yep, I totally did that. I wasn't actually forgot to multiply by 4 the top one instead of 7.
Oh, interesting. Well, those little things happen.
Oh yeah.
These little things happen. So, yep. Cool. Are y'all okay with this? You're good? I know it might be, I don't want to make it too easy here. I want to make sure that you got the concept. Good? Okay, cool. Okay, good. You will be doing this for the rest of the class. These pop up all the time. Even these. It's been a little bit, I know, right? It's not so easy now. But that's okay. So I'm going to try this, but you're going to help me a little bit. What would you use to take a derivative of this big dude?
You can either move the bottom to the top,
Uh-huh.
or you can do quotient rule.
Sure. I'm going to do quotient just because I got the song. Low D high minus high D low divided by the square of what's below. Da-da. You're going to thank me one day. You're going to take a test and say, gosh, I'm so glad I sing it. xy minus 9. The derivative of the top in terms of x. Yeah. Minus the top. The derivative of the bottom in terms of x is a y. And that's it. Yeah, exactly. And then divided by the square of what's below. I don't want to simplify. I guess I could combine like terms. You know what I mean? We could do this. Yeah, oh, good point. Yeah. Only if you have to. I'm going to distribute my minus sign also. And so then I got 3xy. Ooh, nice. Look at that. Right? And so then my final answer, if I had to simplify, would be something like this. Let me flash the answers. Oh, that was the other one. Okay, there we go. Yep, got it. Cool. And then we repeat it for y. It really is not that different for y. Kind of getting bored. But let's do it anyways. I'm gonna do it. I'm gonna be diligent, okay? So low D high. So my derivative of the top in terms of y is a 2. Perfect. Thank you. And then I got my top derivative of the bottom in terms of y is a no. It is a 1x. Very good, x. Yeah, because that was my number essentially. Combine like terms, etc. I think this time I'm also going to cancel the xy thing. So 2xy, 18, 3x squared, 2xy. Cancel. Cool. I am fighting a sneeze right now. Do y'all ever do that? Or you just let it out? It's okay. We got it now. Good? Not too bad. What horrible things are they planning for us now on the next page? Ooh. Ooh. So, that's fun. What are the first two letters of fun? I'm sorry. Anyways. yeah, this one's a lot. And that's okay. Notice that there want second derivative, but in all the different manners, right? Because we can have xx, yy, yx, xy, right? All the different ways. So let's do that. Slowly. So I want to say though, I would rather, if you don't mind, I would rather right now start writing some Newtonian notation so that I'm more familiar with what comes first and second. Okay? I think that this will help us. Again, you have to remember that we're going backwards with the Leibniz stuff. Okay? Backwards. So it is kind of a little weird, but writing the Newtonian helps us see this will come first, then that one. But look, before we keep going, look at the top two. What comes first for them? Both. Fx, right? So we're going to get the f sub x. Oh, yeah, I should probably start naming it correctly. When I do this, I say f sub x. Just fx is okay sometimes, but f sub x is more proper. Anyways, moving on. So yeah, I'm going to find this f sub x first, and then I can take that answer and go two different ways, if that makes sense. So let's just find this first derivative. What would I get there? Yes. Good, good. Times y, the y is still there, yes. Sine of y. Perfect, perfect. Now, remember that this is a number in the front. We're looking at x, so what's the derivative with x? Yeah, negative sign, exactly. You got it. With that same number in the front. Nothing changed in the front. I'm going to rewrite it so I don't have that 0. So this is my starting place for the other two. From this one, we branch out and say xx and then xy. Okay. So let's take the derivative with x again. What would you get for this guy? Sine, well, technically negative sign will go to negative cosine, yes. And we're done with this guy. That was easy.
Wait, Chad, we can factor out a 3y.
Nah. Good point, though. Now, if I looked at this for my y, what would I have now?
Wouldn't that just be 4x? Oh, cute.
Good, good. Because the
That would be minus 3 sine x.
correct. That one's a little weird looking, but the derivative part is right here. Y goes to 1. Everything else is a number. Even sine of x still is just a number. And we keep it because we just want our numbers now. Now, if we had another y, then we would that definitely would go away, correct? But in this case, we're done. Cool. Let's flash the answers. See if we're getting the right direction here. No factoring, I see. So that's good. Okay. Yep. Cool. So then the next one, we both start with an f sub y. So let's start over from the very beginning. Derivative in terms of y, we get?
X
Sweet.
plus, cosine of y.
Mm-hmm.
And then plus 3 cosine x.
Sweet. Thank you. And then again, I branched two different ways here. So I could say yx, and then I got my yy. So now if I jump to the x's, good, good. Perfect. Good. And for yy?
So the x to the fourth would go away.
Good, good.
Then you have a negative sign.
Oh, yes. You're right. Very good there.
And then that would be it because the other one has a x in it, so it would just go away.
Oh, okay. So more zeros. Let's check it out. And indeed. So that was my yy, and that was my yx. Cool. Cool. That was a pretty complicated problem. Can you do that 30 times on your homework? You're like,
Probably they'll take me a while.
Yeah, I know. These are z values. So, yeah, when it says f of x, y, it is equal to z. So we might as well be saying dz dx, dz dy. Yeah, I say d, it's del, but yeah, exactly. I don't see that, and that's the thing going forward. I'm sorry, but you're good with the z. Going forward, the notation is kind of loosey, with the tongue. If you say d, you say del. I get it. I'm gonna try to say del because I should, but it's really just d. If you had a d in there, and sometimes I've seen some weird stuff where they got like a D mixed in and stuff. That, you know what? We'll figure it out when we get there. I mean, it is a little strange, but it's like not a partial derivative, it's a full derivative. Yeah. Yeah, pretty much. Okay, same kind of thing. We just did the last one together, so now y'all have to do this one on your own.
We only have a minute to do it.
Oh, is that the thing now? Oh, we literally only have a minute. Oh, we're done. We're done. We're done. We're not going to do any more. I'm so sorry. We'll come back to that. Thank you. All right, I'm going to stop the recording. Very good.